Today we're going to talk about two topics, transition metal ions and also polyatomic ions. So let's start with transition metal ions. Transition metals are in the D block, and there are a few in the lower left of the P block. They're unique because we can't really guess their charges just by looking at the periodic table most of the time. They have variable charges. So sometimes copper might be +1, sometimes it might be +2. So we have to come up with a system for dealing with, knowing which one it is. But first, let's just talk real briefly about why. The reason I'm going to explain this in vague terms, but the reason is, if you remember back to electron configurations, the 4s and the 3d are very similar in energy. So electrons actually enter the 3d technically after the 4s, but they're very close in energy. And so what happens with transition metals, they have these 4s and 3d electrons, or for a bigger metal it might be 5s and 4d, but at any rate they're pretty similar in energy. So when you have an element like iron that ends in 4s2 3d6, sometimes iron will simply lose its two, what are technically its valence electrons, these 4s electrons, and it will have a +2 charge, because that would be, losing 2 electrons would give you a +2 charge. Other times, iron will actually go ahead and lose those two and lose maybe this little down arrow from this 3d orbital that is paired up. And we don't have to get into too much about why that is. Just understand that this does happen. The S's and D's are very similar in energy, and so losing a 4s electron is not that different from losing a 3d electron, and so that's why we end up with our transition metals having varying charges. So because of this, when we talk about iron, we can't just say iron and know what its charge is. We have to specify using a Roman numeral. So for example, if we have iron 2 oxide, and you do have to know a couple of the Roman numerals, I have a list down here 1 through 7. But iron 2 oxide simply means that this is iron that has lost 2 valence electrons. So if we pair it up with oxide, it's going to be in a 1-to-1 ratio, right? Because oxide is -2. Iron 3 oxide is actually a different compound. Even though it also contains iron and oxygen, it will actually have some different properties. So iron 3 oxide would be iron that has lost 3 valence electrons, or again, maybe it lost 2 from the 4s and 1 from the 3d, but it's lost 3 electrons, so it's going to have a +3 charge. So if you were to write this formula, it's going to be Fe2O3, again, because we have a different charge on the iron. So if we were to work backwards, if we are given the formula and we need to know what that Roman numeral is, how do we do that? Well, first of all, the Roman numeral, we've kind of already said this, but it stands for the charge of the metal. And it only needs to be included if we're dealing with a transition metal. And even among the transition metals, there are actually a couple that we don't include the Roman numeral for, and that's because they never do, they don't actually vary. So if you look at this periodic table here, I've just helium and hydrogen are clipped off, but we don't need them anyway. We're focusing on the metals. Our transition metals, zinc, cadmium, and silver, you can see here are in white. And these guys are transition metals that only form one ion. And this is a similar periodic table in your packet already, but silver is always +1, so you do need to know that. And then zinc and cadmium are always +2. So again, you need to know that as well. Aluminum and gallium, you probably would guess anyway, are always +3 because they have 3 valence electrons. They're in group 13. There are some main group elements, some P block elements that are considered transition metals sometimes, or at the very least we can say that they have variable charges. The most common ones we'll see are going to be tin and lead right here. So we will need to include the Roman numerals for those to indicate their charges. Scandium over here on this particular periodic table is not shaded in blue. We're just going to pretend that it is. In other words, we're going to assume that scandium actually has a variable charge, even though this particular graphic shows that it doesn't. All right, so if it's in color, it needs a Roman numeral, is basically the moral of the story here. So manganese, our first example, manganese is colored in here. It's a transition metal. It has a variable charge. So we can't just call this manganese chloride. We have to figure out what the charge is. And the way that we do that is pretty simple. We know that the total charge on the compound has to be 0, right? All compounds will add up to 0 because the electrons are simply being transferred within the compound. They're not coming from outside or the compound or going anywhere else. So we know the total charge is 0. We also know just by looking at the periodic table that chloride is -1, just like all group 17 elements. And we know that we have 2 of them, so if we multiply, we get -2 as our total negative charge, which means that if the total has to be 0, our total positive charge has to be +2, right? And since there's only one manganese, right, there's an implied subscript of 1, 2 divided by that implied subscript of 1 is, of course, 2. So we figured out that this is manganese with a +2 charge. And so when we write out its name, because it's a variable charge transition metal, we need to include that in the name. So it's going to be manganese, Roman numeral 2, chloride. Okay, let's take a look at the next one, Cr2O3. We're going to follow the same steps. So we know the total charge is 0. We also know just by looking at the periodic table the charge of oxide, -2, right, because it's a group 16. This time we do have to multiply by a subscript, and that's a 3, so our total negative charge is -6, which means, of course, our total positive charge has to be +6, so that they do, in fact, add up to 0. Now, and we do this time have to divide by a subscript on the metal, on the positive ion here, so 6 divided by 2 will give me the charge of each individual chromium ion. And that, of course, is +3. So the name of this would be chromium 3 oxide. Okay? Now, the next one is Zn3N2. I could go through all of that math that we just did for the previous 2 problems, but if you notice, zinc down here is not shaded in, and that's because zinc is always the same charge. And again, it says this on the periodic table that's, or one of the periodic tables that's embedded in your notes packet already, but zinc and cadmium are always +2. So therefore, I don't have to write a Roman numeral. It's actually wrong to write a Roman numeral. I don't want to include a Roman numeral, okay? So because of that, there's no math that I really have to worry about. I'm simply going to call this zinc nitride, okay? Now, if I did the math, I would find that zinc does, in fact, have a +2 charge, even if I didn't have that memorized or didn't have a periodic table that told me that that's its charge. But it's not necessary to do that because in the name we don't include the Roman numeral. All right, go ahead and see if you can pause and try these last 3 on your own. Remember, if it is silver, zinc, or cadmium, hint, hint, do not include a Roman numeral. Otherwise, if it's a transition metal or one of these guys down here in the lower left of the P block, do include a Roman numeral. So go ahead and pause and do that now. Okay, so for the first one, PTS, you should have come up with platinum to sulfide because they're in a 1-to-1 ratio and sulfide is -2. So this must be platinum with a +2 charge. And then Ag2Se, remember silver is always +1, right? So this is simply going to be silver selenide. And then finally, Cu3N, well, nitride is -3, and so if it's -3 and there are 3 coppers, each of those coppers must be +1. So hopefully you had an idea what to do on those 3. Okay, going in the other direction is really not any different from the previous homework assignment. The only difference here is instead of using the periodic table to get the charges on some of them, you're just looking at the Roman numeral. So for example, if I have lead with a +4 charge and then oxide, well, oxide is -2, lead in this case is +4, so we just have to balance those charges. And if we do that, we get Pb NO2. Okay? So chromium 6 phosphide. So this is, again, the Roman numeral is the charge. Don't get confused and think the Roman numeral is the number of chromiums. It's not the subscript, it's the charge. So chromium 6 phosphide would give us CrP2 because phosphide is -3, right? So if chromium is +6 and phosphide is -3, I would need 2 phosphides to balance that +6 charge on the chromium. All right, go ahead and pause and try those last 3 on your own. Okay, we should get GaF3, gallium fluoride. Gallium is not a variable charge metal. It's right below aluminum, and it's always +3. And fluoride is -1. Copper 2 arsenide. Arsenic is right below phosphorus, so it's got a -3 charge, just like nitride and phosphide. So we should have come up with Cu3As2, if that's copper with a +2 charge. So we would be trying to get to +6 and -6 with our two positive and negative charges. And then cadmium sulfide should have been CdS. Cadmium is always +2, that's why there's no Roman numeral. It's right there below zinc. They are both +2. Sulfide is -2. Okay, so polyatomic ions. The prefix poly, of course, means many or several. So polyatomic ion is just an ion that's made up of many atoms. So some ionic compounds, like sodium chloride, are made up of single atoms, sodium, right, and chloride. Those single atom ions are called monatomic ions, right, for the exactly why you would think, mono meaning one. So sodium is a monatomic ion, chloride is a monatomic ion. But we also have entire molecules that have gained or lost electrons, usually gained electrons, which is why most of these are going to be negative. But if we look at it for an example, CO3 2-, that whole thing is one ion, and you can see that it has a -2 charge. That just means that it's gained 2 electrons into its Lewis structure to make it stable. This one over here, NO2 1-, has just gained 1 electron, right? And so the charge is 1-. You don't really have to worry about drawing the Lewis structures yet. We'll get to that later. Just understand that when we look at a formula, we can have a metal like sodium, which of course wants to lose electrons, paired with a polyatomic ion like carbonate. So as long as the carbonate is negative, remember the negative means it's gained electrons, and of course where did it gain electrons from? Well, in this case it gained those electrons from sodium, right? So that's how it became -2 in the first place, by gaining a couple of electrons from a couple of sodium ions. So this formula looks like it contains, I mean, you can think of it as containing 2 sodium atoms, 1 carbon atom, and 4 oxygen atoms. But for our purposes, it's going to be more useful to think of this as 3 ions. In other words, 2 Na+ ions and 1 CO3 2- ion. And the same thing over here. This 3 can be applied to, saying that we have 3 nitrogens and 3 times 2 is 6 oxygens. So we distribute just like, in algebra when you have parentheses. But it's more helpful for us to instead think of this as being 3 NO2- ions, right? So this whole thing should be thought of as like one particle. So this would be 4 ions total, 1 +3 aluminum, and 3 -1 nitrites. Now these are going to be a lot easier to recognize once you have memorized a list of them. List, of course, can be found in your packet. You will be responsible for this whole list. We will have a quiz over them next week on Monday. So I would start making flashcards now, because you're going to have to know the formula with the charge and the name. So on the quiz, you'll be given either the name or the formula and charge, and you have to give me the other one. So again, flashcards or Quizlet or just anything that works for you. Could just be staring at the list and going back and forth or quizzing each other, but these will have to be memorized because it's going to be a lot easier for the rest of the year when we're talking about reactions and acids and bases and more difficult concepts if we don't have to constantly look up the formula and charge and name of each of these. So these are each to be thought of as one particle. So for example, Cn minus is cyanide, right? ClO3 1 minus is chlorate. ClO4 1 minus is perchlorate. And I can talk to you a little bit more about some of the systems and things that, there are some systems in place in terms of how some of these got their names. Generally speaking, if you have more oxygens, like for example, SO3 2 minus is sulfite, if you add an oxygen, it becomes sulfate. Same thing with chlorite and chlorate. But we also have some other weird things that come in, like perchlorate is what you get when you add yet another oxygen. And hypochlorite is what happens when you take a chlorite and take away an oxygen. But probably just for right now, the straightforward memorization is the easiest way to go. Okay, and so the last thing we need to talk about is how to use these in an ionic compound. So if I see a name like potassium hydroxide, then we are going to be able to write its formula because we know the charge of potassium is +1. Right? And if you have your little table out that we just looked at in your notes, you should be able to see the hydroxide is -1. And so those would just be put together in a 1-to-1 ratio. Don't think of this as 3 atoms. Think of this as 1 potassium ion and a hydroxide ion. Okay, that's why the memorization is important, so you start to recognize OH as hydroxide rather than thinking of it as an oxygen and a hydrogen separately. All right, and then barium chlorite. So let's think about what is the charge on barium, right? It's in group 2, so that's going to be a +2 charge. Chlorite, if you find it on your table, it is ClO2 with a 1- charge. So we are just going to treat it like a monatomic ion. We have to balance the charges out to 0. So if barium is +2, I'm going to need 2 - 1 chlorites to balance that out. Now notice what I did here. Because I had multiple chlorites that I needed, I put that entire polyatomic ion in parentheses and then the 2, right? Because this original 2 that was there, that did not mean 2 chlorites. That meant that chlorite contained 2 oxygens. That subscript from the list of polyatomic ions will never change. The only thing that will change is sometimes when you want to have more than one polyatomic ion, or more than one of a polyatomic ion, you have to put parentheses and then the 2. Okay, go ahead and try, see if you can work out these next 4 on your own. Go ahead and pause. Okay, let's take a look at the next one, iron 2 phosphate. So this is iron with a +2 charge, and then phosphate from your list has a -3 charge. So you should have hopefully come up with Fe3PO4 parentheses 2, right? So this is 5 ions, right? We have 3 irons because each of them is +2, so we need a total of +6. Phosphate is -3, so we needed 2 of them to get to -6. Remember, we're just using the least common multiple, just like we've been doing for a little while, okay? So in this case, we're trying to get to +6 and -6. All right, nickel 2 hydrogen sulfate. Be a little careful with this one. It looks like this is 2 things, hydrogen sulfate. That's actually on your list. That's a polyatomic ion. And nickel is +2, and hydrogen sulfate is -1. So you're going to need 2 hydrogen sulfates. Okay, and then the next one was lithium sulfite. So lithium is +1. Sulfite is SO3 and it's -2, so hopefully you said Li2SO3. Now again, I didn't need parentheses here because there's only one sulfite, but hopefully you can recognize or see this as, instead of saying it as 2 lithiums, 1 sulfur, and 3 oxygens, see this as 2 lithiums and then 1 sulfite. And again, the quicker you memorize your polyatomic ions, the quicker that will be to recognize. All right, or the quicker you'll be to recognize that, I guess. All right, so zinc acetate. This one looks complicated, but it's just 3 ions. So zinc is +2. It's one of those transition metals that always has the same charge. and then acetate is -1. And so we are going to need 2 acetates. All of these subscripts inside of the parentheses, they're just part of the formula for acetate. Those are never going to change. We don't have to do any math with them. We don't have to do anything with them. We just have to put the whole thing in parentheses and then decide how many we're going to have. And in this case, it's going to be 2 to balance out the charge of zinc. Okay, going in the other direction is pretty simple. The only thing we have to think about sometimes is we might have a variable charge metal. So keep an eye out for that. So what I want you to do for these last 4 is just go ahead and name them. So see how you can do with that. Go ahead and pause and give them a shot. Okay, so aluminum is not a transition metal, so we don't really have to do anything with this except call it aluminum hydrogen sulfide. You have to recognize that HSO3 is one of your, polyatomic ions from the list. The reason there are 3 of them is because aluminum is +3 and this whole big thing is only -1, so we have to balance those charges. But it doesn't become a part of the name, so we didn't really have to do any math there. The next one is a little tricky because this is our one and only positive polyatomic ion. The rest are negative. But this guy is called ammonium, and he is +1. And so this one is going to be called ammonium nitride. So our negative ion, nitride, just gets the "ide" ending like it has been getting. Nothing changes there. All right, these last 2 are a little tricky because there's some big numbers involved, or big-ish numbers involved. This is vanadium. It is a transition metal, so hopefully you included a Roman numeral. And that Roman numeral would be 3 because carbonate is -2. Again, we just got that from the list. And there are 3 of them, so that would be -6. And so to cancel that, we need a total of +6. And if there are 2 vanadiums, each vanadium would have to be +3. This next one is, or this last one is about as difficult as it gets just because we have a 3 and a 7. And the phosphite, if you looked it up, is -3 charge. Times 7 is -21. So we need the positive charge to add up to +21, which divided by 3 means each technetium is +7. So technetium 7 phosphite. All right, hopefully that all made a lot of sense. If it doesn't, feel free to rewatch it or rewatch parts of it. And we'll talk more about this and review it later.